Let's start for the topic of the balance on transient process. Sometimes we talk about the unsteady state process. Unsteady state process. What is the characteristic of the unsteady state process? Some slides discuss about the unsteady process. Silipan, are you hearing? Silipan.
Yes, Ajahn.
Could you describe about the unsteady state process? What is the difference between steady state and unsteady state? That's all the topic that we talk from the first week until last week. We talk about the steady state process. But today we will talk about the unsteady state process. Could you describe what is the difference between these two systems?
Wait, Ajahn. Wait. Hello, Ajahn. Can you hear me?
Yes.
Yeah. It's like mass and energy on the system is changing with time.
Or steady state or unsteady state?
Unsteady state.
Okay, thank you for your question. That's correct. But if we talk about the unsteady state, that we talk about the mass or energy balance, include or change with time. That's we talk about the mass of the species or total mass or another change with time. That's we talk about the condition or property of the system. If we talk about the mass, in terms of concentration of the chemical or species change with time. If we talk about the steady state, that property is not change with time. As I when time proceeds, the concentration still is the same, not change. There is no mass accumulate in the system, or there is no energy accumulate in the system. It flow in, flow out continually. So let's get this the steady state process. And also this is an ideal system. But in the real system, we cannot to control the system to be the perfect system. It's difficult to be the perfect system. Because generally, it's like the physical, chemical, or thermal property should be depends with time. Maybe some accumulates on time or resist something from the system. Okay, for this case, we will talk about the mass and energy balance. Mass and energy balance for the unsteady state system. I think you know this already when we talk about the mass balance or energy balance. The general equation that accumulation equal to input at generation minus output and net consumption. Previously, we classify into system for the steady state. For the steady state, that we talk this a lot. This state there is no accumulation. No mass, no energy accumulate in the system. Accumulate the system. Or there is no mass or energy depletion or accumulation. But for here, we talk only about input minus output, but generation minus consumption equal to 0. Because we consider the system. But now in this chapter, we include steady state, unsteady state. So unsteady term is accumulation. It may be increased or decreased with time. That means in term energy will accumulate or depletion may accumulate or deplete. That means change with time because it is the transient process or unsteady state. We talk both in the reaction system and non-reaction system. If there is reaction system, term generation and consumption will be improved. We consider both all of this for input, generation, output for reactive system. For reactive system, we will consider 5 of this, but for non-reactive, the generation term, consumption term will be cancelled. This is the case that we will consider. Okay, look at this term. If we talk about the input, that's right, for the mass balance. Input, it should be mass, it should be massless. For this case, mass is in terms of kilogram per second, is massless. If we consider in terms of the small time interval, sometimes we consider small time interval delta t. This is the massless multiplied by delta t, this is the mass in kilogram. If you don't mass it, you multiply the time interval delta t kilogram. Output also about multiply delta t. Generation, generation less of mass generation multiply delta t. Less of mass consumption multiply delta t. It is if we consider A as the mass of some substance shape in the system. The system we call this delta f. Delta f during a small interval time. Okay, for this case, the delta f, delta f, for accumulation or depletion is delta f. Equal to input m in plus generation minus m out minus consumption. Multiply delta t. Multiply delta t. That means the change of mass A in the system. Delta f during a small time interval that we consider from 1 minute to second minute, from 1 to 10 minutes. And this is the change of the system, of the system. And then if we divide this both sides, if we set to divide this delta f, you get delta f divided by delta t. For the get delta f divided by delta t. And delta f means m at t plus delta t minus m at t divided by delta t. And if you take limit, you take the calculus, that you study in the calculus one. You take the limit or definition of limit. The limit at delta t approach 0. If the time interval is very small. Delta t approach 0. This is the definition of derivative. Limit at m plus delta t minus m at t divided by delta t. This is the definition of derivative dm by dt. This is the derivative. dm by dt equal to m in plus r gen minus m out minus r consumption. This is the general equation for unsteady mass balance or transient mass balance. That dm by dt, the change of mass with respect to time, equal to less of mass in plus less of mass generation minus less of mass out minus less of mass accumulation, made of mass consumption. This is the accumulation. It's positive when accumulation or increase. It's negative when the mass is decrease or depletion with respect to time. And this is equation we call it the first order ordinary differential equation or first order ODE. So we talk this in the calculus 1, 2, 3 that we start in the first year. For this case, if you would like to solve for this ODE, you have to know at least one condition. Sometimes in respect to time, the time is initial condition or boundary condition. You have to know what happened at time zero. This is the initial condition. What is the mass at time zero? If you know the mass at time zero, you can solve for this equation. That's why you need this condition at time zero. What is it? Sometimes you can write m at time equal to zero equal to what's right. If you know this, you can solve for this equation. If you have only one equation, you need only one condition. If you have two equations, you need two conditions. You need two initial conditions. It depends on the equation. This is the technique to solve the ODE. We have a lot of techniques to solve. You can change a variable. You use the separation of variable. If you separation a variable, and then you apply the integration. So for that, you can record the technique from the study by calculus. Okay, we give you some example. The first example is we have the stirred tank reactor. We have the reactor. It's stirred tank reactor. For this reactor, we use to produce compound in a liquid phase reactor. For this case, with a reaction in liquid phase, A to R. A is substance, R is reactant. The feed to reactor. The feed to reactor at a rate of V0, this is the rate of liters per second. Volumetric flow rate of the feed. The density of the feed is low, gram per liter. And the concentration of the reactant is Ca0. This is the feed property. We have volumetric flow rate, density of the feed, and concentration of the feed. Feed is A. A0 is more A per liter. The volume of the tank is VA. The volume of this tank, we put the V with the volume of the liquid in the system. For that, this is V, it is liter. Liter. For this case, the vessel may be considered perfect mix, so that the concentration of A in the product stream, we call that the tank. Is it the perfect mix? Well mixed or perfect mix? Like the definition of well mixed or perfect mix. This means the concentration of substance in the tank equal to the concentration in the outlet stream. It is the definition of perfect mix or well mixed. Like the concentration every point, every location in the tank is the same and also is equal to the output stream. This is the definition of perfect mix. If you talk about the perfect mixing tank or well mixing tank, we talk about that the concentration at any point in the tank equal to the concentration at the outlet stream. Ca in this, Ca as outlet is the definition of well mixing. That means the mixing is perfect. Mixing is perfect. Okay. For this sample, the flow rate of the outlet is V per second. The density is low. For this case, we assume inlet and outlet density is equal. Ca outlet and Ca inlet not equal, but Ca outlet equal to Ca in the tank. For this same. And for this case, we define the rate of consumption of it, because if A is reactant, consumption equal to Kca from this. This is the rate of consumption. If we talk about A, we talk about the consumption. If we talk about ice product, we have 200 generation. Okay, for this case, the rate of consumption equal to Ka. Ka is more per second per liter of the reaction volume or reactor. Okay, this is the rate of consumption. Okay, for this we have more assumption of fluid, feed, tank constant, and product. Maybe it have the same density. recipe. The liquid inlet, liquid outlet, and liquid in the tank have the same density for this case. For the case, we assume low is constant and low is constant. Okay, the question is, write the differential balance on total mass and write the difference on A, side, on A. And then expressing the balance in terms of the variable shown on the photograph. Okay, for it, we have three. Balance on total mass, balance on A, right? Balance A. Then express balance in terms of variable, in terms of V, in terms of A, in terms of load. Okay, for this case, we will consider this equation. Like sometimes we have to exploration is equal to input generation minus consumption minus output. For this case, we have no generation if we talk about it. If we talk about it. And then if we talk about the total mass, if you remember at the top to you about the mass balance, if you talk about the total mass, no generation and no consumption term in the total mass. Or in atomic balance, there is no generation, no consumption for total mass or atomic balance. For total mass, accumulation equal to input minus output. If you talk about the species balance or A, accumulation equal to input plus generation minus output minus consumption. But for A, there is no generation because A is limited. If we talk about product, no consumption, of input generation output. Okay, for this we will talk about the total mass first. Total mass first, I talk to you, no generation, no consumption for total. That accumulation equal to input minus output. Okay, we consider for it. Okay, mass index. Mass index we define as m in gram. The mass of the substance index equal to volume of the liquid or volume of the liquid multiply density of the liquid. V is the volume of the liquid multiply load with multiply gram per liter. Liter multiply gram per liter, you get gram. This is the mass. This is the mass in the liquid. Okay, and then you define the accumulation term. Accumulation term mass per second. This is change of mass with respect to time. dm by dt. The first term accumulation equal to dm by dt. What is it? M is V low, dV low by dt. If we know from the assumption that low is constant, low is constant, you can move low out of the electric. You get low dV by dt. Okay, this is term of accumulation. And the second term is input. Input, we look at the input also gram per liter, gram per second. So this is the unit of dm by dt. dm by dt, m is mass, t is times mass per time. You know the accumulation is mass per time. And then input also the mass per time. This is the input term. Input term. It should be volumetric volume. V0 is liter per second. Multiply density load gram per liter. This is the input. How about the output? Output should be volumetric volume, but output volumetric volume multiply density V load. Okay, you substitute all of three terms into this equation. You get low dV, low dV by dt equal to V0 low minus V low. V0 minus V low. But for this case, low is constant, you can cancel low. You get dV by dt equal to V0 minus V. V0 minus V. And for this case, you have to know at least one condition. For this case, we know the initial condition at time 0. equal to V0. V equal to V0. Initial volume for the state. Initial volume for the state. This is the total mass balance. That's right. dV by dt equal to V0 minus V. V0 minus V. As sometimes we have some question. If V0 equal to V, what happens? If V0 equal to V, dm by dt equal to 0. That will be the statistic percent. For V equal to V0, that means flow is equal to 4 out. This is the assumption of steady state. dm by dt or dv by dt equal to 0. For that case. As for this problem, no, we got the input not equal to output. For that. This is the answer. Okay, the next we talk about the mass A balance. Mass A balance. Balance on mass A. Okay, for this case, there is no generation. Because this is the reactant. No generation. Generation is for product. If you get accumulation equal to input minus output minus consumption. Input minus output minus consumption. Moles of A is the reactant. Volume multiply CA. Volume of the liquid multiply concentration of A. Later you get more A. You get more A. And then you can express term of accumulation is dVCA by dt. dVCA by dt. This is the accumulation. Because we talk about the VCA is the mass or mole of A in the reactor. The accumulation of A in the reactor is dVCA by dt. The next term input V0 multiplied CA0. V0 multiplied CA0. Output V multiplied C. Output V multiplied C. And consumption KCA. KCA multiplied V. Because from the problem statement, the rate of consumption equal to KCA. But the unit is mole per second per liter of the reactor volume. First, we have to multiply V. That has multiply. Okay. Now you know the substitute of this whole term into this equation. dVCA by dt equal to V0 CA0 minus VCA minus KCA. This is the differential equation for the mass balance of reactant. Accumulation equal to input minus output minus consumption. And for this case, if you would like to solve this equation, you have to know initial condition. That you have to know the concentration at time 0. CA equal to CA at time 0. What is the concentration at initial time at time equal to 0? If you know this, you can solve for this equation. Right now, you write the general equation for total mass. This is for total mass. This is for mass balance on reactant. You can solve it for product also. Okay, you can express the mass balance of the reactant and total mass with respect to volume, with respect to flow rate, with respect to K. K is the reaction constant. With respect to initial, not initial, this is for inlet concentration. This is the outlet concentration. The outlet concentration equal to the concentration in the tank. This is function of volume. But for this case, CA at time 0 is different. This is at inlet. CA0 for at inlet. CA at time equal to 0. Okay, the next time we can define the consistent or transient equation in terms of the integral balance. Previously, we talked about differential balance. If you consider the integral, you can look at the differential equation. The differential equation, and then you multiply both sides with dt. And so you get df equal to m in dt plus r gen dt minus m out dt minus r cos dt. This is the integration from initial time to the later time. You can integrate from initial time to the later time. For example, you integrate from t0 to tf. You take the integration. Integrate dm, you get dm tf minus mT0 equal to integrate T0 to TF M T0 to TF RJ minus T0 to TF M out minus T0 to TF R. This is the integral form or integral balance. You look at the equation for the example. In the second example, we talk about the water balance on a city. Like we have the water level in municipal reservoir has been decreasing very rise. There is concern that the drought could continue for another 60 days. The local water company estimate that the consumption rate of the use of its water by community approximately 10,000 liters per day. This is the consumption rate. And next, the conservation should estimate that the rainfall and stream draining into the ocean. What is this? This term, the rainfall or stream drainage into the ocean, this is the input. The water input to the ocean. Coupled with the evaporation from the reservoir to water input. This is the net water input and output. And T is the time in day from the beginning of the drought. At this time, reservoir contain atomic and overnight is of water. For this step, you have to write the differential balance, and then the second integrate the balance calculate the volume of the water in the reservoir at the end of the 60 days. So for this case, you can look at the full form of the mass balance that I talked. dm by dt equal to m in plus r n minus m out minus r cos. This is the phi term. So for this case, the first term is accumulation. dm by dt. Also dm by dt equal to d rho v by dt. If we consider rho is constant, the water inlet, water outlet, water consumption, it is the same density. If we assume the density is constant, you can move the density out of the density to get rho dv by dt. Rho is kilogram per liter. dv by dt is liter per day. Okay, and the second term, m is less of mass is less of mass. For this case, you know, right, the net rate of mass is net of mass is substitute how to low modify this. And outlet is low modified 10 power 7. This is consumption term, which is not the rate of consumption. This means the rate of the water flow out to the community. This term means the flow out of the water to the community. The meaning of this calculation. You see that for this case, there is no reaction, no generation, no consumption, because the system is flow of water out and water accumulated. But the term consumption means the rate of municipal use of water. That means the flow of the water out to the community, not the consumption based on it. Okay, for this case, there is no generation, no consumption, but there is finally you get the equation is dV by dt equal to 10 power to the potential at t divided by 100 at 10 power 7. Because the density is constant, you can cancel this. And then from the problem statement, you know the initial water inlet, the reservoir. The initial in the reservoir at the beginning we have 10 power 9 liters of water. For this case, you know the initial condition at time 0 v equal to 10 power 9 liters. Okay, now you know the volume change with time, that you know the initial volume. You can solve for this. You can solve for this. Okay, the rest that you separate the variable. dV equal to 10% at 2 divided by 100 and at 10 also dt. And then you can take the integration. dV equal to this term dt. You integrate v0 equal to v60 from time 0 to 60. Application the integration at v60 minus v at time 0. For this term, you can separate into terms. Integrate 10 over 6 multiply e power minus 2 multiply 100 dt and 10 over 7 dt. Integrate this two terms. You know v0. You can solve for v. But v0 equal to. If for this case, you can solve. You get the volume of the water at 60 days is 4.45 multiplied 10 power 8 liters. This is the technique to solve. So for that case, you have the differential equation. The basic technique that you can separate the variable. dt, okay, this time. Is it dv equal to some term divided by dt. Because all of it is constant. Then you can integrate. This is the separation of variable technique that you can study in the calculus. Okay. The second example, we talk about the chemical reaction. For this case, we have the no chemical reaction. We have two equations for that. This chemical reaction, for this no chemical reaction. Okay, for this case, we have the solid tank. I have the tank. Sometimes to make the solution. This tank is 12.5 cubic meter tank. Is being filled with water. Okay, the water at the rate of 0.05 cubic meter per second. This is the flow of water with this. And also, at the moment when the tank contains 1.2 cubic meter water, that means at initial time, at time 0, this tank includes the water 1.2 cubic meter. 1.2 cubic meter. Okay. Bottom, we have some tube to leak the water. Instead, the water is flow out the tank. Flow out the tank. For this case, we know the related of the water is approximately. This is the less of water leak 0.0025 milliliter per liter. Milliliter per liter leak from the. The question is why the mass balance on the tank. And then you can solve for dV by dt. What is the equation of dV by? And then solve the equation based on the function of time. First step, we have to generate the mass balance. For this case, we have only water flow in and flow out. Flow in and flow out. There is no generation or no consumption because there is no reaction. Only water flow in, but in and out not equal. You can constantly treat the unsteady system. You know the initial volume of the water is 1.2 cubic meter. 1.2 cubic meter. And the maximum volume is 12.5. It is the volume of the tank or the maximum volume that the tank can use the water. The water can stay. Okay, the first step you record the mass balance that we derived already. dm by dt equal to m in gen minus n out. There is no generation, no consumption. No generation, no consumption. For this case, the total mass balance of water balance is the same. The same because we have only water. The total mass water balance is the same. We have only one. Okay, total mass balance m equal to low water volume of liquid. For this case, we can assume low water is 1,000 kilograms. The first term accumulation should be d low v by dt and low constant f low dv. This is the accumulation. How about input? Input is low multiplied volumetric flow. Volumetric flow is 0.5. Low multiplied 0.05. This is input. How about the outlet? Outlet it should be low multiplied flow rate. Flow rate is 0.0025 multiplied t. If low multiplied 0.0025, you get 0.002. You substitute this equation. You get dv by dt equal to 0.05 minus 0.0025. The low is cancelled because we multiply this low. So you get this equation. And also, you know the initial volume is 1.2 cubic meter. Right? You know the initial volume. You can solve for it. But you know initial volume. You know the equation. Okay, from this equation, you multiply dt both sides. Both sides. Cancel. You get dv equal to 0.05 multiplied 0.0025 dt. And then you can integrate from the initial to final v or to any v. And the initial is 1.2 cubic meter to v times 0 to time. You can integrate. I think you can integrate this. This is the basic. Integrate dv, we get integrate constant multiply dt, we get integrate t dt, we get t squared divided by 2. Okay. This is the equation after you take the integration. V equal to 1.2 multiplied plus 0.05 t and that's 0.00125 t squared. This is equation after you solve for the differential equation. Okay, for this case, you know time 0 equal to v by 1. You can check the constant. Or you can check by differential this. By this equation. You take dv by dt of this equation. It's equal to this one. If it's equal to this, okay, confirm your answer. This is the answer. That's our answer. Okay, for this case, you can plot volume with respect to time. Volume with respect to time. Do you have any problem? That's about 98 or 50 or 59. We can say the volume is minor. If the mathematics is possible, but in physical meaning, there is no meaning. When you talk about the mathematics and the real world, you have to check. This value is negative value. It's not possible. But that is not possible. The real meaning should be 0, not negative. So negative. But that's here. That means at time about 57 minutes. 57 minutes. 57 minutes. The volume is 0. But that means the volume is 0. All of the water in the tank is poured out. That's right. There is no water in the tank. But at time about 57. Okay, for this case, we can write this equation in two cases. Okay, the first case, the volume equal to 1.2 plus 0.053 minus 0.001253 squared. We can do it only in this time. 0 to 57. We can do this equation. Because when time greater than 57, the volume is negative. This is not possible. At time greater than 57, the volume should be 0, not negative. And then you can conclude that V equal to 0 at time greater than 57. This is very important when you use the mathematics. Okay, you know the mathematics, and then you have to check the possible. But this is not reality because there is no way to negative volume. For this case, you have to take the answer by this. The answer should be like this. That's it. We have to play. That you solve from the mass balance should be okay only for time between 0 and the time for greater than 57. The volume should be 0. It is the very important technique you have to check. And you have to check with the physical meaning. Okay, before we move to the next example, I would like to